All right, welcome to our third and final video for this week. Lastly, we're going to talk about how to use double-headed arrows to show the steps that are happening in a chemical. It's called showing the mechanism. This is going to be a central skill for the rest of the course, so something that you really have to, something that will never ever go away. We're going to start by talking about ionic reaction mechanisms. We did offhand mention radical reaction that are initiated by homolytic bond cleavage. One electron goes. We're not going to do that yet. We're going to focus on ionic reaction. And we're going to have four main ways that electrons will move in a reaction. These will be nucleophilic attack, loss of leaving group, proton transfer, and arrangements. So this word, nucleophile, should be familiar to you. We talked about it last time. So a nucleophile, remember nucleo means nucleus, like positive, phile means love. So something that loves positive things. So these will be those that have an extra lone pair to give, particularly those compounds that have a negative region. That will be the nucleophilic site, and that will go and attack, or those electrons will form a bond with another molecule that has a positive region that the attracted to. So last time we spent a lot of time talking about at the end how to identify a nucleophile versus electrophile. That will be very important. Remember, a nucleophile is basically just a base. Got a lone pair, preferably it's negative. More willing it is to give that lone pair and create a bond, more reactive it is, nucleophile. So here's an example of a nucleophile, the bromide ion. It is negative. It has lone pair of electrons that it can use to donate to create a bond. And here we have on the right an electrophile. We can tell because it is a carbocation, it is positive. And not all nucleophiles are negative and not all electrophiles are positive, but they're at least partially, right? But this is a full negative and a full positive. And so this now these two electrons, we put the tail of the arrow starting at the electrons. You have to start at the electrons for this nucleophilic attack. It will end at the electrophilic site, the positive part where the electrons are attracted to, and then that will be the formation. So you'll notice this is a one arrow type of move. The arrow starts where the negative charge is, it ends where the positive charge is, and the electrons are shared and create a bond. This is so nucleophilic attack can appear to occur in two steps. This is particularly true when there's a resonance type situation. So you guys know from our old resonance days in previous chapters, chapter 2 in particular, we would identify this and we would say, oh, this is a pi bond between two atoms of differing electronegativity. So we'd say, okay, well, these electrons go up here, and this is resonance structure. This guy right here. See very explicitly that the carbon here is three bonds now and no lone pairs, so it's positive in formal charge. This oxygen has one bond and three lone pairs, negative. And so that's basically what's happening here is this arrow. So although a nucleophilic attack can occur can have a one arrow movement there, it can appear to occur in two steps when you have this type of a situation here. Again, we know this is the nucleophile because although it's not negative, it's partially negative. So this oxygen here is partially negative. It's pulling electrons from the hydrogen and from the carbon, so it has a partially negative charge here. Likewise here, this oxygen, as we can see by using that resonance structure, it's pulling electrons its way, so we have a partially positive charge here. So this is the electrophilic site. It's attracted to electrons because it's positive. This is the nucleophilic site. It's got a lone pair of electrons that donate to create a bond. When it does, this carbon now has 4 bonds and no lone pairs. This oxygen has the extra electrons from the pi bond, so it's negative. This oxygen is now making 3 bonds and has 1 lone pair, so it's a positive formal charge. So all that stuff from chapter 2, notice we're just busting through that real quick. So hopefully you got that down, or if you were having trouble, we're able to at least review in that week after the exam. That's really important for anything that you're having trouble with, to go back and maybe redo some of those homework problems or do a few more. Make sure you're really solid. This stuff I'm not going to be going into as much detail as I did back in chapter 2, but we're going to see this stuff all the time. The alcohol is the nucleophile in this example. With it attacks the carbon with a positive formal charge. The arrows show the movement of electrons, right? So that's why it's important to remember we start where the electrons are. You can't start an arrow where there aren't electrons. So you have to start them where the electrons are. Show the movement. The second arrow can be thought of as a resonance arrow, right? Like I was describing it. Okay, so that's the first arrow pattern arrow pushing pattern that we have, is the nucleophilic attack. The second one is the loss of the leaving group. And so that is also a 1 arrow move. So this occurs when we have a bond breaking. So in the case of the loss of a leaving group pattern, the arrow is going to start on a bond that's going to break. And it's going to end on the atom that's taking the electrons along. So in this case, this bond between carbon and bromine is breaking. So we start the arrow there, and the electrons are ending up on the bromine. So after we're done, this carbon is only making 3 bonds and has no lone pairs, so it has a positive formal charge here. And the bromine is now a bromide ion. It now has 8 electrons around it instead of its normal 7, so charge. Now that's the leaving group is gone there. So what about this here? So this is a very complex set of arrows that is showing the loss of a leaving group as well. And again, you can see how this can be complicated when you have significant resonance, right? And so we can see here that in this case, the loss of the leaving group, this is actually occurring right here. So this is a 1 arrow movement. If we were to draw the remainder of the structure, but I'm not going to draw all the lone pairs. So after this chlorine leaves, if we drew that separately, we'd end up with a positive formal charge right here, because this carbon had 4 bonds and no lone pairs, but now it has 3 bonds and no lone pairs. And then we'd also have the chloride ion left. We can draw that over here, but not as important. And so now we have this weird resonance situation, right, where we have several different resonance steps. We have a pi bond that is allylic to a carbocation, and then this produces a carbocation here, and so the pi bond allylic carbocation, and then at that point we would have a nitrogen here that has 3 bonds and no lone pairs that have positive 2 formal charge, so we have a lone pair. So these are all resonance arrows that are really showing. So this is meant to demonstrate that sometimes as you get more advanced, you'll see not only in the case as we saw of the nucleophilic attack here, resonance happening or resonance being displayed also by the double arrows, but here the loss of the leaving group can also be indicated along same time as resonance occurring. So we're not only doing resonance like we did in chapter 2, but we're also applying these mechanistic rules where bonds are breaking. Here this bond broke. The rest of these don't involve bond breaking, right? They're all electrons just moving through p orbitals. They're resonant. The third type of move is called the proton transfer. This is always a 2 arrow move. We studied this in chapter 3 actually, so we've already done a bunch of proton transfers as a part of the acid base chapter. Uh, but you'll have some Lewis base again. Uh, making the lone pair here, the negative charge, a lone pair electrons here. This one is actually neutral, but here this lone pair is going and making a bond with the hydrogen, and then the two electrons behind. And the result is that now we have this oxygen that has 3 bonds and 1 lone pair, so it has a positive charge. We can also have a proton transfer from the solvent. So you'll notice here, well, hydronium and water are being written above the arrows too here. This is something you're going to see more and more, where we have a molecule that we're focusing on and another molecule that we're not. Often the one we're focused on is called the substrate. We're going to call that in the next chapter. We're going to start using that word a lot. And then this would be called a reagent. So like something we're adding to it. So this is just another way of saying these two react with one another. But often the substrate is kept in focus while the reagent is sometimes just drawn above the arrow in OChem. So we can also have a deprotonation, so that would be basically the reverse of this reaction. Now the water grabbed the proton, and we have left behind. So that's one way you're going to see these reactions written. Another way that you'll see them written is you'll just see that the proton was lost. And that's probably not the preferred way to show it most of the time, but you can say, oh, this proton was lost, some other base grabbed it. So that's one other way you might see it in the book. And when it's shown that way, it's just shown with one arrow. Now, again, like when we saw for the previous two with the electrophilic, the nucleophilic attack, and the loss of the leaving group, with proton transfers, there can be resonance type things happening at the same time, right? So in this case, it wouldn't make sense here to make, so when we do this 2-arrow pattern, it wouldn't work perfect because we'd end up making a double bond here and this carbon would have 5 bonds. And so you have to watch out for that and be aware of when resonance is present, right? Probably the best way to do this would just be to show that here the negative charge is initially on the carbon here, carbanion. Clearly this is a terrible structure. If we want a negative formal charge, it should be on the oxygen. But what we see here is an allylic lone pair. So we do the 2-arrow allylic lone pair step from resonance from chapter 2. And then we have a double bond here. And now this oxygen has 1 bond and 3 lone pairs. So it has a negative formal charge. Now the last type of step is called the carbocation rearrangement. And so we've been studying carbocations for a while. This is just a picture of a carbocation. So we see this carbon is making 3 bonds with no lone pairs. So that means its steric number is 3. Which means it's sp2 hybridized, which means it has 1 unhybridized p orbital. And that's right here. And so this is what a carbocation looks like. Now, when you have a carbocation that is adjacent to another carbon atom, this carbon atom, you'll notice that there's a way, these are very close, and this hydrogen is overlapping with this carbon's hybridized orbital. However, it's a little bit different in this situation in that the hydrogen can jump over and make a bond here to this neighboring carbon very easily by donating this electron density into this empty unhybridized p orbital. And this is referred to as hyperconjugation. When you have a carbocation like this in this case, and you have this kind of sideways overlap. When this hydrogen jumps over, now this becomes an unhybridized p orbital, and now this becomes an sp3 hybridized carbon. So this effect is called hyperconjugation. In reality, this carbon isn't fully sp3 hybridized, right? And this one isn't fully sp2 hybridized. This hyperconjugation is saying these two carbons are kind of both sp2 and sp3 hybridized. They're kind of in between. Now, hybrid conjugation and induction can both be invoked to explain this stability trend. So in the case here, we can think of stability here for the carbocation being the greatest here on a carbon that is attached to the most other carbons. And the reason why this is because for every other carbon that you have attached next to this carbocation carbon, you have some hyperconjugation. You also have the induction of the pull of the electrons. You can pull some electrons from the neighboring carbons, which is much less true for hydrogen. First of all, for hydrogen, there's no p orbital, so you can't have hyperconjugation like we saw in the last example. Also, for hydrogen, it does not pull electrons, so like the carbon. So remember, the electronegativity for hydrogen is 2.1. For carbon, it's 2.5. And so the inductive effect of the carbon is significantly greater for carbon than it is for hydrogen. And you may have a carbon that's right behind it as well, further increasing that effect. So the result is that the tertiary carbocations are the most stable. They spread out that positive charge the most. Whereas if you have a secondary carbon, which is attached to only two other carbons, this is less stable, which is less primary is even less stable, and a methyl carbocation is the least stable, so I'm the most reactive. Remember, when we have a small, tight charge somewhere, that makes something reactive, right? So with this tertiary carbocation, this positive charge gets spread around a little bit because these carbons can donate a little bit of electron density to kind of minimize that positive charge there. The opposite is true in methyl. These hydrogens just cannot give up their electrons. The electrons are in the bond. They don't have any other electrons to spare. There's no stabilization of this positive carbocation. So because we saw that we can have a carbocation rearrangement, though, the hydrogens will move in such a way so as to produce the most stable carbocation, which will be, tertiary or secondary. So this results in what's known as a hydride shift or a methyl shift. These are both carbocation rearrangements. And the carbocation rearrangement involves one arrow. The arrow starts from the bond, which essentially is breaking here between the carbon and the hydrogen, and then goes over to the carbon that the hydrogen will bond to. And so it ends here at this carbon. And so this hydride shift, this would be made spontaneous or more spontaneous by the fact that here this carbocation is on a secondary carbon attached to two other carbons, whereas after the hydride shift occurs, now the carbocation is on a tertiary carbon, which is significantly more stable than the secondary one. Methyl shift can also occur. So if you have a carbon on a neighboring carbon right next to a positive formal charge, the methyl can move over, and you end up, and it will be driven by the same stability here, the stability of the tertiary carbocation. Once this methyl moves over, you have a tertiary carbocation, whereas before it moved, you had a secondary carbocation. The shift can only occur to an adjacent carbon because it's due to that hyperconjugation, which only occurs between the sideways overlap of adjacent orbitals. And the shifts make the carbocation more stable by making it a tertiary carbocation. So let's take a look. So this is a full-on mechanism. So we're going to be using these steps that we just learned, the 4 steps, which are the nucleophilic attack, the loss of the leaving group, the proton transfer, and the carbocation rearrangement. We're going to use those 4 types of moves to show all the steps that occur in an ionic reaction. And this is going to be referred to as the mechanism. So here we have our first full mechanism that involves several of these different types of arrow pushing steps. So the first one involves a 2-arrow process. And notice at the end, a bond is made between the oxygen and hydrogen, and the bond is broken between the hydrogen and the bromine right here. And so this is going to be a proton transfer. 2 arrows here. Okay. And then we have an arrow that starts from a bond, and that bond is going to break, and this water will leave. And so this is the loss of the leaving group. Next, we have this methyl moving over, and the carbocation moving from this secondary carbon to this tertiary carbon. This is a rearrangement. Or if we want to be more specific, a carbocation rearrangement. Finally, we have the negative bromide ion forming a bond where the positive formal charge on the carbon is. So this is the nucleophile attacking the positive carbon. We know it's a nucleophile, it's negative, it has lone pairs to give, which is giving to a bond. We call that a nucleophilic. And together, these steps represent the replacement of an OH group with a bromide. And these individual steps make up this reaction. A lot of the times, as you saw previously, we can have lots of different steps in a mechanism. Sometimes a single step will include more than one of the arrow pushing pattern, especially when they occur simultaneously in time. So there's one type of reaction in which a nucleophile attacks and a leaving group leaves at the same time. So this arrow here shows the nucleophile attacking this positive carbon. We know this carbon is partially positively charged because the chlorine has a very high electronegativity. It pulls electrons its way, so it's partially negative over here, and it's partially positive over here. So this partially positive part is the electrophilic site. The nucleophile, which we can tell this is a nucleophile because it's negative, the base. Remember, nucleophiles are bases, and it has electrons it can donate as a lone pair to make a bond. So this one here is the nucleophilic attack. And simultaneously in this reaction, when the nucleophilic attack is occurring, also occurring is the loss of the leaving group. So the chlorine is leaving as a chloride ion. So there are lots of mechanisms that involve these 4 patterns. We're going to be using them over and over. So you have to get very good at identifying which of these patterns will occur and are occurring. There are certain rules you have to follow to make sure that the way you're using the arrows is correct. So just like we had rules back when we were describing resonance, there are certain rules that we use to describe the way reactions are occurring. So in this example here, we have a nucleophilic attack occurring, just like we saw in the last slide here, to this carbon. So a bond is being made from this oxygen to this carbon, and simultaneously this chlorine is leaving chloride. This is the correct way to draw the arrows. What you would not want to do is draw an arrow like this. So this first arrow is okay. This second arrow is not. Why? Because the electrons are not coming from the carbon. This carbon does not have electrons to give. The electrons are coming from this bond, which is breaking. And so we need to indicate that the arrow starts here, bond, and not here. You must be very, very careful with the way you draw your arrows. The arrows need to come from a place where there are electrons available to move, like a bond or a nucleophile. It can't come from this carbon atom, which has no electrons to give. The arrow has to begin on electrons. It has to end on a nucleus. It's either making a bond or those electrons are just being attached onto the nucleus. So again here, this arrow here is coming from these electrons. It is forming a bond with this carbon. These electrons are coming from the bond, but the bond is breaking, and now they are a lone pair. Avoid breaking the octet rule. So you never want to give carbon, nitrogen, oxygen flowing more than 8 valence electrons. They just don't fit. So here, this oxygen cannot make a bond to this carbon without another bond breaking. So if this is going to occur, then the chlorine must be leaving simultaneously, right? So if we were to just make a fifth bond here and not break this bond, that would be exceeding the octet rule for carbon. So be very careful, just like before we were doing resonance arrows. You need to be careful about violating the octet. Your arrows finally should follow the patterns we outlined. So there were certain patterns for resonance that did not involve bond breaking or bond making, just describing the movement of electrons in unhybridized p orbitals, right? You had to follow the rules that made sure those electrons were going, moving around between unhybridized p orbitals and bonds weren't breaking. Or when it comes to the arrow pushing rules, they need to fall into these 4 patterns. So we had 5 patterns for resonance. We have 4 patterns for reaction mechanism and these arrow pushing rules. We have nucleophilic attack, we have loss of leaving group, we have proton transfer, we have rearrangement. This is a nucleophilic attack, this is a loss of leaving group. Those are arrows that work. This is not an arrow that works. Sure, the pi bond could be a nucleophile. It could go attack a positive area and make a bond with it. However, this carbon is not positive or negative or anything. It's a carbon that has 2 bonds to hydrogen, 2 bonds to carbon. If a bond were made here somehow, this would make 5 bonds. Also, or it would just add really what's showing here, this just would add a lone pair to this carbon and make it negative, and it would have 10 electrons around it. That would exceed an octet. So following these patterns here, make sure that you don't do something unreasonable. So let's now do another example where we're now, instead of identifying what arrows we have, we're writing the arrows. Okay, and so we can see that in the difference between this reactant here, this product, is that there's now a bond between carbon and oxygen. So what's happening is we're having a nucleophilic attack. Also notice that this oxygen is negative now. So we're going to start from a lone pair and we're going to end here where a bond is. Now we can't just use one arrow in this case because that would mean this carbon would be 5 bonds. However, we do have a resonance arrow we can add. There is a pi bond here between 2 atoms of differing electronegativity. So we can use resonance arrow there to show that electron right there, and that avoids exceeding the. So now we have this intermediate here, and then all right, and so that's that reaction right there. In the next one, we've got another example. Sorry, I think this arrow is a mistake. So we got one more example here, and in this one we have a proton transfer. There's no hydrogen attached to the oxygen here, but in the end there is. So this is grabbing the proton, this base, and these electrons. So in the end, we have an oxygen with 1 bond and 3 lone pairs. It has a negative charge. And then this electron is used to make a bond. So now this oxygen has 2 lone pairs, and it has a hydrogen. So 2 bonds, 2 lone pairs. And so that's how you write in the arrows. Show each step. So here, this was a nucleophilic attack and resonance, and this one was proton transfer. Let's take a look now at bad arrows. So for each of these below, let's identify what's wrong with these arrows. Okay. Well, when we look at this one, in this case, first of all, okay, in the products, it's showing a double bond here. However, this arrow is going to this carbon atom. So what this is really doing is this is making a 5th bond to this carbon atom. This would not produce this structure. Instead, it would produce this one. So we'd have this, and then this OH would be attached. And so we'd have an OH, and there are already 2 hydrogens here attached to this carbon. So we have an OH, and we have a hydrogen, we have a hydrogen. This has this exceeds the octet. So this exceeds octet. So this is really bad. So this is an illegal move. We can't do. You could attack this carbon and make a bond here because then we have the resonance, right? So this is an sp2 hybridized carbon. It could make 4 bonds if these electrons are shown this way, right? But this is an illegal move. This one here. So first of all, the first arrow is bad because what's happening is we're losing the bromine. So it's being the loss of a leaving group. So this arrow should start here and end on the bromine. That. And now the bromine, say minus Br, it's gone. And now this carbon was bonded to a bromine, a hydrogen, and 2 carbons. Now it's just bonded to a hydrogen and 2 carbons. So it has 3 bonds and no pairs. It has a positive form of charge. This arrow is bad because the arrow always has to start from electrons. It's not starting from electrons here. I'm not really sure where this arrow is starting. It's on badly. In fact, where it's intended probably to start from is this hydrogen. So what's going on is a carbocation rearrangement. In fact, it shouldn't start from this hydrogen. It should start from this one right here. So if we have this hydrogen here, this arrow, so this would be a carbocation rearrangement. This bond is now bonding over this carbon. And so now we have in carbon, we have 2 hydrogens attached, not just 1, 2. This carbon has 4 bonds, but this carbon was bonded to 1 hydrogen and 3 carbons. Now it's only bonded to 1 hydrogen. And so it has no formal charge, or it has a positive 1 formal charge. And so finally, these arrows are bad as well. So here apparently this is supposed to be indicating it's removing a hydrogen to make the double bond. These arrows are bad. Instead, what's going on is this is taking this hydrogen like that. Arrow. This is taking this hydrogen proton transfer. And now these electrons are now going over to form this bond. And now there's a, and so that's the proton transfer. The other way we could show it is we could say that there was a negative, like right here, and then the arrow says that, oh, this. But we can just show those electrons are involved in the. Yeah, so these are fixing those arrows. You need to watch out for things like exceeding octets and not starting arrows where there aren't electrons. The arrows should always start where electrons are present. They should always end somewhere where they will make a bond or leave a lone pair. When you encounter carbocation, you have to think about what carbocation rearrangement would lead to the most stable result here. So in this case, for this one, we look for the adjacent carbons. So the adjacent carbons are right here. There's 2 adjacent carbons. And one of these has 2 hydrogens attached. So 2 bonds to carbon, 2 hydrogens. The other has 1 hydrogen. And you now want to think about if there's a hydride shift or a methyl shift, which would produce the most stable carbocation. And that would be if this hydrogen here shifts to the left, we would end up with a tertiary carbocation. So the carbocation rearrangement that will occur here is this hydride shift right there. Hydrogen would make a bond there, and we'd end up with a carbocation right here, and the resulting structure would be three bonds now, and they're carbocation right here. that is the hydrogen shift that would occur. The other hydride shift would produce only a secondary carbon. So this hydrogen shift is likely. So here's the picture of the shift, positive formal charge. Methyl group, just like I drew. So let's do the same analysis for the molecule below. We want to identify the adjacent carbons. So the adjacent carbons are here, 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 and here. These have 3 hydrogens. This has 1. Here's the hydrogen right here. Here's the hydrogen. So it would, for this one, it would mean that this will go like this, and there will be a hydride shift there, and we'll end up with this new structure. We'll have now this carbon no longer has a hydrogen attached. It's making 3 bonds and no lone pairs. So it's a positive formal charge. There's one other thing to think about, and that is that now we have an allylic carbocation. So not only will we have this structure, but we will have resonance as well. So this is a 1 arrow resonance move here, and then we would draw our resonance structure. So the other structure that we're going to have is this one right here. And now this carbon is making 4 bonds with this double bond, but this one has 3 bonds right above my head here. And so these are 2 resonance structures. So these would be both equally stable. So you also have to think about resonance when it comes to carbocations, right? Here we have 2 stable carbocations. That's really important because these will be 2 stable intermediates and result in 2 stable products if a nucleophilic attack happens afterwards. So be sure to keep in mind your resonance from 2. Now for our double-headed arrows. So we've talked a little bit about double-headed versus one-way arrows, and I said something like, well, if you decide that the equilibrium constant is like 100 or 1,000, then you would say that there's a lot more products than reactants. Or if the equilibrium constant is like a 1/1000th, like 10 to the minus 3 or 10 to the minus 2, then the reaction might be irreversible and leftward direction towards the reactants. There's no hard and fast rule about whether you use a double arrow or a single arrow. You'll see sometimes your book will use like a bigger arrow one way and a smaller arrow the other, just to indicate that one way is favored in equilibrium than the other. And so why are some reactions drawn as equilibria and others as a one arrow? It's just a way to show how much at equilibrium, how much of one side will be favored versus the other. In this case, what we're saying with the reversible arrow is that there will be significant amounts of at equilibrium of this reactant and this intermediate. However, after the methyl attaches here, this reaction will produce almost all products and very, very little reactants. So we say this reaction is irreversible. So remember, we related delta G earlier to K, and we said if delta G is very negative, then there will be a lot of products. Like if it's like -5 or something, there'll be a lot of products. If it's very positive, there will be a lot of reactants at equilibrium. With this nucleophilic attack here, here's another example. So we have a nucleophilic attack. We have the result of this attack here would be now this carbon will be making 4 bonds. This oxygen will only have 1 lone pair and 2 bonds. This will have a positive formal charge to it. And if we're talking about the reverse reaction, in this case, this would just be the loss of the leaving group. So the mechanism for the reverse reaction would just be the opposite of the nucleophilic attack, be the loss of the leaving group. And then we would have our initial reactants back. And the question is, how do we judge whether this will be reversible or not? Whether we draw a one-way arrow or a two-way arrow, and we can think about the relative stabilities of the reactants and the products here. Um, they're both not particularly stable. The products are a little bit more stable because the positive formal charge is on a carbon rather than an oxygen. Oxygen is very electronegative. It would prefer a negative formal charge. This is also driven forward by the fact that we have greater entropy here, although it does take some energy to break this bond. Right? So here's the ways that we're going to kind of codify this so that we can get some kind of idea of whether of what side this will be favored in equilibrium. So if the attacking nucleophile is also a good leaving group, it will be a reversible attack. And so we will say this is reversible. In this case, the like we're looking here, the reverse reaction will have a low energy transition state. That transition state in this case would involve the formation of this bond, which is, we can tell it's low in energy, kinetically favored to some extent, because this is going to be attracted to this positive formal charge. Right? The reactants and products of the reaction will be similar in energy, allowing significant quantities of both to exist. And this is true here too, right? Neither of these are particularly stable relative to one another. They both have a positive formal charge. They're both unstable intermediate. And so this reaction will be easily reversible. If we have an attacking nucleophile that is a poor leaving group, meaning that it's completely unstable as a separate group. So this here, this nucleophile is a methyl ion, okay, and this is going to be very, very unstable. So we know this. We can evaluate this based on REO. Remember, we use REO to evaluate the stability of conjugate bases here. And this conjugate base is extremely unstable. It wants to get something positive so bad. Remember that the pKa of like methyl. So if we're talking about CH4 losing, H plus and making this ion that we have right here, the pKa for this acid is about 50. So losing this proton is really, really terrible. These are very, very unstable. And so we know that based on our REO analysis. And you would use the same type of analysis. Water, for example, quite stable. Not very particularly basic, right? However, this is extremely basic. It really, really wants a proton. The pKa here for the methyl is really, really low or really high. It's a terrible, terrible acid. So this is a extremely weak acid, which makes this a great base, right? And a great base is a great nucleophile. And then in this case here, the nucleophile attacks, and now this has got quite a bit of stability to it. Although it has a charge, the negative formal charge is on an oxygen, and this leaving produces this extremely unstable nucleophile. And we can figure out that stability based on REO. So we have a massive difference in stability. And so equilibrium is really, really going to favor the right here. It's not going to want to produce this, go left and produce this highly unstable nucleophile. So based on what we've learned in chapters 2 and 3, based on the stability of ions related to resonance and where the negative charge should be on an electronegative atom, everything we've done in REO to evaluate the stability of conjugate bases will help you to determine. So consider the loss of the leaving group. This occurs. Get this product here. I'm going to do a double arrow here because we can probably pretty easily see that this bromide is a nucleophile. It's going to be attracted to this positive formal charge. So the reverse reaction could totally happen. Would be quite spontaneous. So here the reverse reaction would be a nucleophilic attack. Of course. That said, a reversible arrow is appropriate here. Why? Well, because the bromide is a good leaving group. It stabilizes the negative charge very well. I can tell based on ARIO. If I think of the if I think of the conjugate acid HBr, this is a very strong acid. It's very okay with stabilizing this charge. So we can say that the bromide ion is a very weak base because the conjugate acid is so strong. By ARIO, we would say atom. Atom is big, it's electronegative, it stabilizes the charge. And so this would be very reversible because the negative ion here is quite stable. So it would definitely be okay with this or okay with making the bond again. So here's where ARIO comes very handy. Not just for acid, it's a way of evaluating the stability of negative ions, which can help you decide how spontaneous a reaction will be in a certain direction. Now here's a proton transfer again. As I said, using pKa values and using ARIO can be very valuable for evaluating the stability of anions, especially when a proton transfer is occurring. So we can see here that this alkylamide ion is going to grab the proton and leave one behind, so there's a proton transfer. And again, for the alkane, the pKa is 50, whereas for water it's 15.7, much higher. We write a one-way arrow here because these pKa's are so huge. We know this is hugely basic. It really wants the proton, and it's going to get it. At equilibrium, though, lots more, very little. However, if we look at tert butoxide, which is drawing it out, this is something you're going to see a lot too as we move forward. Is you're going to see these shorthands here. Tert butoxide. This is a tert butyl group, which we learned in chapter 2, and here's the O minus. And so when this takes the proton here, it makes tert butanol, which is just a shorthand way of saying this. And the pK is a lot different here, right? In this case, the difference in pKa's between this acid and water behaving as the acid and giving the proton is only 3. And so we could write a double-headed arrow here. If you wrote a one-way arrow, this wouldn't be so bad here because they are different by about 2, right? About 100 times difference. But this is much more reversible than the first one. As I said, there's not a hard and fast rule for when you write a reversible arrow, whereas if you don't. But if you're aware based on using ARIO or pKa's in a proton transfer mechanism, which side of the equilibrium is favored, and if you know it's favored a lot more, like in this case, this side, the right side is favored a lot more, then you definitely want to write a one-way arrow. So the book here is saying, as a guideline, if the pKa difference is 10 units or more, that's when your book will draw one way. I'm not super picky about this. This is what your book says. When I was taught it, it was different. It was a lot less of a threshold. Really, I wouldn't be too wound up about what is exactly a threshold for when you write a one-way arrow. But when it's very, very clear that you're going to have a lot more product than reactant, or a lot more reactant than, like in this case, with a huge difference in one-way arrow is really appropriate there. Carbocation rearrangements are generally considered irreversible, like this one here. Why? Well, this one has a tertiary carbocation, and see this carbon is attached to 3 different carbons. This one has a secondary carbocation. This carbon is attached to two different carbons. The tertiary carbocation is much more stable than the secondary. So in the case of carbocation rearrangements to a more stable tertiary carbocation, we generally draw one way. Finally, when we're deciding what will actually occur practically in a reaction, we should consider Le Chatelier's principle. This is something you learned in the equilibrium part of Chem 151. We should think about basically what happens when this reaction is occurring, because we can use that in our favor. This reaction, we could draw a one-way arrow, and the reason why is because when this reaction occurs, nitrogen is being produced, and assuming it's occurring in an open container, the nitrogen will bubble away, and it will go away, and so that will remove it from the reaction. Every time it's removed, that means that the reaction will shift to the right to replace what was removed, and that's what Le Chatelier's principle says. The reaction will shift in the direction that fixes any disturbance in the equilibrium. And the disturbance in the equilibrium here is the nitrogen bubbling away and flying out of the reaction container. When this is removed, the equilibrium shifts to the right to replace it, and this will cause the reaction to continue to go in the forward direction. And that's a trick that's often used in industrial or synthetic chemistry to make a reaction continue to produce products. So this reaction would continue to produce this amide ion for us as long as we let the nitrogen escape, because that will shift this equilibrium to the right. And so that's something that we'll use sometimes in the lab. And so at this point, we've talked about how to identify nucleophiles and electrophiles, how to evaluate based on entropy and enthalpy, to what extent a reaction will go. And finally, we've used double-headed arrows to show the breaking and the formation of bonds, also referred to as a reaction mechanism, and how to evaluate the equilibrium favored side depending on the type of reaction occurring. And so good luck on your homework for week 7 this. Please let me know if you have any questions. Have a good